And I think as software engineers, and let's say we think of doing this ourselves, Ratko. So like, is this hard maths or is this just matrices and multiplication? That's it.
Exactly. It's
in any of the sentence, right? Like, let's say if I change this sentence, let's remove the from the beginning, right? Like, will the sequence of the tokens, the chunks will remain the same? Like,
it really doesn't matter. This is what something which we train on.
If you have a vocabulary of 50,000 words, then every word, first word is 0, second word is 1, third word is 2, create a hash.
You can maybe make it as an array.
No, the thing you said is.
Let's go.
Bas. So, hi guys. Today I'll be demystifying transformers. So I have my friends here who all are working in software development for quite some time, but they are using transformers or LLMs in their daily life, but do not really know what's going under the hood. So I think this session would be just a refresher for them to actually know what's under the hood and how these models work internally. So before anything else, let's look at a model. We have ChatGPT open up here, and let's ask it a cat set mat and complete this. Yeah, so I think this is no less than magic. If anyone sees it for the first time, he would be like, how can a machine generate new words which make sense? Without wasting any more time, let's get into the class. So we'll be going over around 10 to 11 topics, which will be mostly about how a transformer model works internally and what happens before it and after it. So the very first question I would like to ask you guys is, why do we need transformers? Do you have any answers?
It's a good use case, very useful in coding other things. Do you say transformers or do you mean LLMs?
Okay, so let me rephrase it. So very first question should be, let's start from very fundamental question. How do machines understand words? Do anyone know?
Binary, 0 1. How do machines understand words?
Yeah, how are machine able to understand words and then generate them? That makes sense.
If they cluster them together and try to make sense of, if there are 5 words, they try to.
That was some of the very first thought I think researchers back in 1940s, 50s get. So yeah, it started with rule based. So like in languages we have nouns, pronouns, adjectives and stuff like that. It started with this. They gave a set of rules to a machine that needs to obey them in order to generate senseful words. But it was really not generating anything, because even if you know all the rules, there are very more niche nuances you should know to be able to understand or generate language. Then, as Hakirat said, that we can do this based on statistics. Let's say we have a large dump of data, we put the better model and see how do words form, what are the similar patterns we can follow, and we can learn by that. That worked. We generated a few sentences from that, a few words from them. But yeah, we know it should fail really soon because the model's just memorizing the pattern and not actually generating anything. So yeah, post that we enter the neural network era, which I should not talk much about, but give you a bit of history what it is. So we are still focusing on language modeling. So let's keep image and audio aside for now. How do languages started to work for using neural networks? So very first thing that came into existence was sequence models, but let's get started with RNNs. RNNs stands for recurrent neural networks. They are neural networks which contains memory, and they are sequential in nature. So let's say we have a word, we have a sequence of words, a cat sat on the mat. How a RNN would process it is like it would take a, and then it would store it in this memory, then go to the next word, store it in the memory, get in the next word, store it. So by the time we reaches mat, it doesn't even remember what was the first word or who sat on the mat. That was the very first problem which arose from RNNs. So yeah, to fix this, we need longer memory, as you guys should have guessed it. So yeah, enter LSTMs. LSTMs introduce the gating mechanism. So like we were doing in RNNs, in LSTMs what we do is that every word we let it correct itself, we add a gating function, which basically let it, should I remember this or should I not? So it can, in the same example, a cat sat on the mat, it can, let's say he chooses not to remember ya and the, but chooses to remember cat, and also chooses to remember mat. Since he has compressed the context so much, he now has some sense of who sat on the mat and what it is. But still, as I discussed earlier, that this is sequential in nature. So which means we have to process every word by word, and in this era of parallel computing, which is very slow. So I think now we can get onto the problems. Similar to the cat sat on the mat and it was comfortable. The first problem we discussed was the words can have multiple meanings. Here it could refer to either the cat or the mat. So to get the full sense of it, our model, or let's say for now our black box model, should understand what does it refers to and how do I figure that out. Same goes for comfortable. It could describe the cat's feeling when it sat on the mat, or let's say just the mat texture is comfortable. So yeah, we as a human instantly recognize it, that yeah, here it is in sense with the cat and not the mat, but for machine it's quite difficult. The next problem we discussed, context matters across long distance. If I forget what cat is by the time I reach mat, then there's really nothing I'm getting out of it. So yeah. Next thing is order matters. A cat sat on mat versus mat sat on cat completely sounds different words. Are completely different sentences, but they have the similar words. We know order matters, but not machine. So we need to figure this out. We'll be solving these three problems across our session, and by the end, we'll have a very nice insight of how these LLMs or the models you see on ChatGPT, Claude internally works. So yeah, order works, but how do we do parallel processing, making sure the order works? So we have to solve parallel processing, we have to solve long context, and we have to solve that each word gets meaning of every other word, so it can correlate to anything it is. Okay, so yeah, let's check our first milestone, which is why do we need transformers. At this stage, do you guys have any questions?
So we need transformers because architectures before them did not have long memory.
Yeah, as we discussed, they were forgetting stuff when, yeah, in place where they should remember that this refers to this, they might forget by the time they reach there.
And they were sequential, they were slow.
Yeah, so each word processed by one. So the cat on mat. So it stores the history for the while it processes the word cat. Then it stores the history for the cat while it processes the word sat on the mat. So this way it can forget what the previous memory was and how do I allocate it properly.
Makes sense. Does it make sense to understand LSTMs, RNNs architecture and build them anymore?
You should not really get into depth, but if you are really interested into field, you should understand how to do backpropagation, which is the core algorithm which follows neural networks. It is an algorithm which is used to train all these big models, which is at its core very simple differentiation formula, which is done over a long chain, sequence of chain, becomes something which is very valuable to us now. So yeah, if you want to get deeper into this, you should understand what backpropagation is, and then you should just go down the history, how does RNNs came into picture, then LSTMs. The math might make sense for some people, but let's say for average software engineer, it doesn't really give, it's of no matter if you want to learn it or not. You should just have a high level insight of what we have earlier, so that you have some context of where we were and where we are right now. So yeah, this checks our first point of the list, which is why do we need transformers. So is that clear to everyone? Yeah. Okay. So yeah, before we proceed any further, I'd like to show you the architecture which is involved in all these language models. It has changed over the times, but it started with this. It is a simple your transformer block, and here we pass our input and here we receive our output. We will go on each of these one by one, and by the end of it we'll have a complete flow how a word enters from here and we get the new generation. Okay, so let's get into it. So I would like to ask you guys, what is a word?
A word is a combination of tokens.
Yeah, it is somewhat right. For us humans, it's very intuitive to understand what words are, but let's say how do we make machines to understand the word? So what we can do is, let's say we have the sequence of the unhappiest players running quickly. We can divide them into word by word and then do something with them in order to make the computer understand. Or we can do what GPT or new models do, is tokenize them. Okay, so here I would like to ask you guys a very simple question. Why doing this is better than taking the whole world? Like, why are we...
That's better because maybe, in English we have like happy and unhappy, right? So that will help to like distribute that. Also maybe like different tenses.
Yeah, exactly. Here, if we do unhappiest, we only have a single word which would have a single token, and then all the things which will be single for it. Now let's say we divide it into unhappiest. Now we have three different tokens which will let's say in some different context un is used. Now it already has its vocabulary, so it would know that un is used with something which is not that. So this is why subword level is best. It is not like this is not the exact thing which is followed right now. Every big model company has its own tokenization thing, but yeah, this is what we started with.
In any of the sentence, right? Like let's say if I change this sentence, let's say let's remove the from the beginning, right? Like will the sequence of the tokens, the chunks will remain the same? Like will the first token will always be UN and the second one will be HAWT?
No, the sequence really doesn't matter. This is what something which we train on. So we'll get into this at later part of the video, that how in training we give it all the data, and while we use it for inferencing, we just give it the initial tokens so that it proceeds further to it. It doesn't matter if we remove anything from here. It's just our training data or any data.
So my question basically is that can, like in any case there will be a token that is generated which is, let's say, UNHA, and then double P is another token.
So like here we are using, let's say, a subword level algorithm which divides the word into randomly subwords. Let's say we have a different algorithm, it can be anything, which divides into, let's say, it gets into more deeper of these computer architecture and divides the word into H, and we can have bit level things, like each character can be a different token. So yeah, everything can be. It just depends on what you want to use and how different company perceives it.
But if you use subword level only, तो ये तो पक्का है ना कि अगर द हट गया तो नेक्स्ट टू विल बी UN ओनली एंड अगले चार विल बी HAPP ओनली. ऐसा नहीं होगा कि वो UN ही उसकी वोकैबुलरी में UN इज अ टोकन, राइट? ऐसा तो नहीं कि UNH इज आल्सो अ टोकन.
The UN is a token, but let's say there's another word which starts with UNH and it's a bit longer, then the algorithm might be doing on, let's say, 3 letters per word or 2 letters per word. It can be a different token.
So basically what if I have something like it's raining outside, let's take an umbrella. So in that case, umbrella will be represented as an entire word as a token, or like there will be like differences, right?
Yeah, there will be differences. If we are on word level, umbrella would be a single token. If we are on subword level, our tokens can be then umbrella or umbrella.
So it's like
tokens.
phonetics, right? So
yeah, here I would like to show you what GPT-4o uses. So if we go to this tokenizer.Barcel app, it's a nice thing someone has made. So yeah, your sentence was?
It's raining outside, let's take an umbrella.
It's raining outside, let's take an umbrella. Yeah, so here we can see it divided into 8 tokens. So GPT-4o uses the tokenizer, and it is basically each word is given a token ID. So model knows by token ID, not by each word. So each word is then transformed into a token ID. Here we can see an umbrella. Umbrella is a whole token. Yeah, so umbrella for GPT-4o is a single token.
What if you write a lot of gibberish? Will every sentence be convertible into tokens?
Yeah. If you guys are focusing here, every space is a token too. So that's a nuance. Yeah. So let's put any gibberish.
Okay.
You can see we have many different tokens. We do not really know what's the algorithm behind these. Yeah. But you can get a sense of it, that either it is a word level, either it is a subword level, byte level, sub-byte level, anything like that.
And like what does the vocabulary look like? It has like all these indexed out, like all these words,
Yeah. So
combinations indexed out.
before we start to train a model, we make a vocabulary of how many things or how many these tokens do we want to keep it. It started with something like GPT-3 has 50,000 of vocabulary. So yeah, every one of these is unique and already indexed. Okay, and the tokenization, which we just discussed. As you guys were able to see, each word was converted into a token ID. Okay, yeah, I have put the same picture here, that hello world, how are you, is transformed into the same 7 tokens, including the space as a token. Okay, now we have numbers for different tokens, which we are saying token ID. Okay, so for this 7592 token, what do you think it will represent? Hello or goodbye?
Hello.
Why?
Yes.
At this point, we really do not know. After this whole process of training, each word or each token would be relating to something. But yeah, now, so we can see our next task which we have to do. We have to relate every token to an individual word. So let's say we have hello world and the tokens for it are 7592 and 1917. We need a way that we can, what we do say, we can match this token with its word. So how do we do that? Do you guys have any idea? How do we give these numbers a meaning?
Are you asking about the data structure or something else?
Anything.
So basically, if you have a vocabulary of 50,000 words, then every word, first word is 0, second word is 1, third word is 2, create a hash.
We can maybe make it as an array.
No, the thing you said is that is used for converting them from actual words to these tokens. Now I'm asking, how do we incorporate information or meaning of those words into these tokens? So like let's say we have a word hello and the token for it is 1. Now how do we make sure that this 1, or how do we incorporate the meaning of hello into this 1?
We need a lot of data.
Okay, so we need some kind of structure or pattern. Let's say it a structure or a representation of this word which can be mapped to this token ID. So do you guys now can make sense of what do we actually need?
I mean, we get the problem, but we're not able to figure out how.
Yeah, fair enough.
I have one question. Like you are saying, we are also including spaces in the token or whatever it is, but won't like having spaces in that increases the amount of words which GPT we have to give it to
Yeah,
index.
it did.
But isn't it a waste? It's like for a single word, what if I have to index 2 words, 2 spaces, 3 spaces?
But if you do not add any spaces, the language would not make any sense or would be too hard to read.
Also because like if you don't have space, then like it will not know if that's like substring starting
Yeah,
or that.
exactly. That answers your question. Cool. So now we have to incorporate the meaning of the words into these tokens. How do we do that? So we have a word named embedding. We'll start to get into word embeddings now. So we are done with tokenization. What do we get with it? We have a word. Now we can map into a certain token ID. We have a predefined vocabulary which have all the words listed, all the tokens listed and their token ID. Now the next step is how do we incorporate the information of that word into these tokens? Enter embeddings. How I would like to explain you guys is as a translation layer. So like all of you guys write code. We write JavaScript, Python, C++, Rust. The computer doesn't understand what we are writing. So how does it able to do what we are writing on it? So what we are typing it, the computer understands it. How does it do that?
We have like finite state machines, right? With those, it gets.
So basically we have compilers which compiles down our human readable code into machine readable code. This is exactly something what embeddings do, and that's why I've called them the translation layer. For each token ID or for each word, they translates them into a vector. Vector is, for now let's assume vector is just a list of number in a space. We all guys know what a vector is. It's something which points into direction and has some value for it. That's the vector for it. So now what we are saying is for each word we are defining a vector which after the training will incorporate the information of this word. Now you might have the question that at start, how do we do that? How do we incorporate the meaning of words at the start? Like we do not know anything and numbers are just anything random. So how do we do that? We actually initialize from random things. So we randomly initialize all the values in our vocabulary for all the words, and these words or these vectors after the training from our backpropagation algorithm are changed and matched to their actual meaning. Cool. So yeah, computer only understand number, so we would like to transform them into some of the same form which here we are doing for vectors. So like cat will have this vector. I'm showing only 4 dimensions here, but in reality it's 12,000, 24,000, a lot of dimensions. Okay. We have discussed this. Each of the word has its correlated vector, and this word also has its token ID. Cool. So yeah, can you guys notice something here? Like cat has this embedding, word embedding, dog has this word embedding, apple has this word embedding, orange has this word. Can you see anything similar?
Yeah, I think like animals, they do have like closure, and like
Exactly.
fruits, they also have like closure,
Yeah.
right?
So animals have closure values, fruits have closure values, but yeah, if you guys can see, cat and apple do not have any matching or closing values. that's something very, that's what word embedding gives us. It gives us an idea of what does it mean. So here, by just looking at numbers, we were able to know that cat and dog might be something of this same group, which here is animal. So cat and dog, they both are animals, they are both fruits, and unrelated concepts have very different numbers. Cool. So let's imagine a 3D space. We have vectors. We can have a cat vector here, we can have a dog vector here. Oh, sorry, the dog vector will be in the same direction of cat vector, and the fruit vector will be here. If we have a lot of these words, we will have a lot of these vectors. And if we consider each word as a single point, at this image, at this part of the plane, I would have a cluster of all the animals, whereas this part of the image, I'll have a cluster of all the fruits. So that's the crux of word embeddings. It defines or gives meaning to word, which is after the whole process of training, but yeah, is a very crucial steps here. So here's I've put something from the 3B, 1B videos. Like each word is shown as a vector which is pointing into a different space. Cool. Okay. Yeah, you guys must have heard of this famous algorithm of word to vec, and I would like to share one simple example from it. So I can show you guys in code later too, but yeah, if we have a king vector, let's say after we train something, we have a vector for king, we have a vector for man, woman, and queen. So now if we just apply simple vector mathematics or vector formulas, if we subtract man from king vector and then add woman to it, it would give us something very similar to queen vector. So this gives us that words understands each other, and the vectors have now their information of what they actually mean, and we can do all sorts of these matrix multiplication or subtraction addition to get something which we do not want or which we want. Cool. So now we are done with word embeddings. We learned how a simple word is given a token ID and how this token ID is incorporated with all the information of the word. Do you guys have any questions? Cool. Let's move to next thing. We have a problem here which I would like to call the position problem. We discussed these both a bit before. A cat sat on the mat, a mat sat on the cat. The order of the word is very meaningful here. Which, if we just give word embeddings, so what would we get for the same sentences? Each of these would have the same vector. But now how do we make sure that we have the position information too in this? Any ideas?
So basically they would also lie in like really close to each other, right, in the vector space, in the same cluster or something.
Here the cat has a vector, but since we have the vector of a cat, that same vector would be here too. Now how do we make sure that in this sentence cat came before and in this sentence cat came after?
For this particular example, since we are storing the spaces as well, right? Cat doesn't have any of that trailing space in the second one.
We have a tokenization algorithm that takes the first space and not the last space.
Okay.
I think it's like more towards like, cat can sit on a mat, like cat can sit on a mat. Like I don't think like the other one like contrary makes sense at all.
Yeah, but for that we would actually need to make all these understand what everything means, which we haven't right now.
The answer to chalo we know is like you add another index to the vector. My question is, why isn't the transformer architecture smart enough to know this? इसमें हम एक-एक करके feed नहीं करते क्या? उसको खुद को नहीं समझ आता क्या?
Yeah, so you are pointing to a very special problem. At start we discussed that how RNNs and LSTMs were all sequential model. They were like, if we are going for a word, then only that word is going through the whole pipeline. But what is special with the transformer, we can have a sentence here, all of these separate tokens get into the transformer at the same time. Since this is happening in the transformer, we need to make sure we are doing something to keep the order of it, else it would be just messed up. Yeah, so a very easy answer for this is positional embeddings. What we are gonna do, we calculated word embeddings for every word. Now we are going to do some smart steps so that we can add the position information of every word to itself, which would also be a vector. So for position 1, the vector could look like this. For position 2, the vector could look like this. And we are going to add this into our word embeddings. Together they both make the first step in our whole architecture, which is known as the embeddings.
So where are these, like where is this sine and cosine wave information stored? Is this like the previous example that you showed? This slide, is this like stored in here somewhere?
Yeah, the information of the position will be transformed into a vector. So now we have a vector for our position, and previously we saw the vector for our word. We simply just add these both for the first word, for the second word, for the third word. Now we have the information of the word along with its position. Now we can pass it on to the transformer. Since transformer work parallelly, now it also has the sense of what the word is and how far or sooner it is in the sentence.
So this contains information of what, like
Yeah,
in which like meaning it lies, and then it also contains the information like what is the relative distance between each of the word it has.
So this is basically a point from the cosine or sine waves. That is it. We transformed it into a vector, and now that vector would be added to our initial word embeddings. That would give it the sense of positions. Any questions? Cool. Now we are done with embeddings, both our word and positional embeddings. What I showed you guys was sine and cosine embeddings. These were used for a very long time at the start, but at current times we use something which is called rotationary positional embeddings, which uses some more insights from geometry, but it's the same thing. It is still used for encoding the position, but yeah, it's a bit more efficient. Now, I would like to take you through the whole flow of the transformer or the LLM. We start with a sequence of word. We tokenize them, then we end up on the stage of word embeddings. Each word is transformed into its word embeddings, and now we have a sequence of word embeddings. We now add positional embeddings to it. Now we have a sequence of word embeddings which also contains positional embeddings. Now here comes our transformer, which I have put as a magical black box. It does some mathematical computations, smart mathematical computations, and what we get is the next word prediction. I've shown the same thing in the diagram. These are the embeddings we just talked on. They are just our word embeddings added to our positional embeddings, which are passed down to the transformer model, and we get our output. Let's get a more deep dive of it. Let's say we start with this vector. This is the vector which contains our word embeddings and the positional embeddings. We pass it to the transformer. We get this output. Here I put a block which is known as linear transformation. So at the start I showed you guys that we have a vocabulary size. What this exact block does is that it changes this vector to the exact shape of the vocabulary we have. So now we are making sure that we do not get lost or get higher or lower values than our initial vocabulary. So yeah, we are just making sure that we are back to our vocabulary size. After that, each word, let's say these words mean this. So world has a score of 4.2, has a score of 3.8, and so that. Now these are really not making sense to any of us. Like, how do we choose what word should I put up there and not? So yeah, what we do is a simple softmax. So this is a mathematical operation. What it basically does, it takes a list of number and makes sure that some of these all numbers should come to 1. So yeah, it just suppresses all of them, so to make sure that sum of all these is 1. And how is that helpful? It is helpful like this. So for world, it showed us 0.45. Now we can just translate that to a probability, which would come out of as 45%. And since these all compute or adds together to 1, we have a total of 100%. So yeah, this makes much easier for us to work and choose which word should I predict next and which word should I not.
Why can't we just pick the long, जो सबसे बड़ा है? That will be the answer, right? Or do we need?
Yeah.
The final goal is to probabilities. Yeah. Okay, basis पे we'll pick the highest probability. That's the next word you are predicting.
It's also done for a lot of numerous reasons, for numerical stability, to make sure the words don't go out of bounds or gets too smaller. So yeah, to make sure that these all things are in here. And for further stuff, like I think you guys have used a lot of APIs, and in there you set temperature and sampling methods. So yeah, if let's say you set temperature 0, which we call as greedy decoding, what it will do, it will just take the first thing out of it. But let's say you want the model to be a bit more creative. How do you make it more creative? You let it choose somewhat of these lower probability values. So a higher temperature will make these words get a higher probability, and that is done via the softmax operation. So this softmax operation also has a parameter as T, which stands for temperature, which controls this. So that's also an information for it.
Can you repeat the third step? Third step.
Yeah.
Yeah, the third one. Yeah.
Okay, so we have this transformer output. Now this can be a vector which is very long and can be longer than our vocabulary. Since we have a fixed vocabulary size, we want to make sure that all these tokens or all the information we have got are now back to the initial size of our vocabulary, so we can point to a certain word or a token. So yeah, that is the exact same thing it is doing. It's just making sure that now everything is back to its vocabulary size so that I can work further. Without it, we will not able to get that this whatever this token is means the world. Just that. Cool. Okay, we are done. I've given you a very high level view of what happens when we give input and get an output. But yeah, we have to still discover what the magical black block is. Okay, now let's enter into it. This is what a transformer look like. It is just a continuous layer of attention followed by an MLP. MLP is what I think you guys, let me just put up image. Yeah, you guys have seen a lot of these images. This is exactly what an MLP is. All of these small green globes are called neurons, and these together are called a layer. So MLP stands for multi-layer perceptrons, which means that we have multi-layers of these neurons or perceptrons. That is it. Okay. So yeah, we have a bunch of these. I think in the initial paper, which is known as Attention is All You Need, we have 12 of these attention heads. So attention followed by MLP, attention followed by MLP. This is what inside of a transformers look like. What I'm about to present you guys is my idea of what I see transformer as. So I like to see it as a highway. Here we give our input word embeddings, and here we get our output. Let's forget this for now. I want to see it as a highway, or we call it as a residual stream. Yeah, residue is what gets collected over the time, so it is called a residual stream. Here our attention block I have referred to as a social network, because what it does, it talks to all the words internally and gets something out of it, which is the meaning of the words. And I've called instead of layer norms there should be MLPs. Yeah, MLPs. What MLP is an individual processor. The information we get from attention is then processed by these MLP. Since in transformers, attention holds a very small part of our whole, like we hear 20 billion parameters. From all of it, attention only contributes of 20% of this parameters value. So yeah, we can see that attention have very less parameters, and it does not really is doing much things. While MLP constitutes of the other 75% of the neurons, because it is doing a lot of mixing and matching of all these words to make sure that we are concretely able to identify that this words mean this and it is attaching to this. What I put is layer norm. We do not have to get much deeper into the mathematics of it, but it is put here just to make sure that we are not going out of bounds, the numbers are not getting very small. This is just a numerical stability steps which we are doing here. So for every attention layer, it is followed by this numerical stability layer norm, and then we have our MLP followed by layer norm, followed by attention, followed by layer norm. This is the crux of it. Yeah, as I mentioned, the layer norm is just a quality control which makes sure that we are stabilizing all the numbers and no number is outgrowing or becoming very small. Cool. I have given you what the magical black box constitutes inside of it, and at this stage if you guys have any question you guys can ask it, because after this we'll be getting into the details of what attention means, what MLP means, and how things happen inside them.
Can you repeat the attention part? What does it actually mean, like attention?
Oh yeah, we'll get into this right now. Cool. So yeah, let's get into attention. How does attention actually works? You guys must have heard of things like query, keys and values, what they actually are. So yeah, let's demystify them. I put a picture down there which basically means that in attention what really happens is every word, every token, I would like to say, ask a certain questions to every other token including itself. So it asks a bunch of questions. Hello ask a question to world, hello ask a question to how, to make sure or to understand what I mean and what I could give, what information could I give to others. Every word does this for itself and all the other words in the sequence. Attention. So yeah, we just discussed what softmax is. It is basically a way we can translate a list of vector into a list of probabilities. So yeah, we can remove that from here. Now we are going into what query, key and values are. I put a nice diagram here of what query keys and values are. So remember, what we input to our transformer is a list of vector which we get from word embeddings, and then we add positional embeddings to it. So at this stage, that same word embeddings is divided into 3 parts. So we are basically just cloning it 3 times and putting a query, key and value. Now you must ask, why are we doing this? Each of these will differ. It will differ by the weights. Since we are using the same word embeddings, we are using certain different weights for it too. Weights are basically just parameters the model can tune itself via the process of training. So each of these are same word embeddings, but just have a different weights attached to it. Sure. But now let's get into the formula and break it down. We have our query and keys. I'll get into what query, keys and values mean after this, but let's just get done with this. So we have, let's say, now we have our 2 representation of the word. We just do a dot product between them. Now, do you guys understand what dot product means? Cool. It basically tells us about the similarity. The greater the score, the closer the words are to each other. The lower the score, the words are far apart from each other. So at this stage, we are just doing that. We are just checking if the query and keys are correlating to themselves or not. And this by decay is another numerical stability steps we do to make sure that we are staying under the limits. So we just scale it by the dimension of keys. That is what we call here. Then we have our softmax here to convert them back to probabilities. And here we have the third clone step of our word embeddings, which is called as values. We again do a dot product or a matrix multiplication between them and get our final output of the transform attention weight, which is known as attention weighted sum. Cool. Now let's get into the query, key and value framework. I'd like to show you guys this as a social network thing. Yeah.
One question. Can you go back to the formula? So if dk and t are the part of parameters, right?
What?
Why if t is also variable, right?
Oh, this T is not temperature.
Oh, it's not there.
This is transpose.
Oh, okay.
Yeah. These are matrices. Yeah, these are full matrices. This constitutes of our initial word which we just give a. I mean, each row of the vector is a sentence. Oh, each row of the matrix is a word. Yeah, and together it is a whole sentence. Yeah, correct.
All 3 are like that?
Yeah, all 3 are like that. What's different between them is the weights that's attached to them. So like this has a weights q, this will have its own weights key, and this will have its own weight value. And these weights are what gets updated after training. So yeah, after the training they mean different things.
Let's say I give a transformer a sentence, or I ask it to calculate attention of that sentence. So it will be a number, right? So I give it like, what is your name, for example. So that sentence will get embedded thrice, like in 3 different matrices. Or are they contribute, like they do different things?
So yeah, I think before you came we discussed about what word embeddings and positional embedding means. So let's say we have a sequence of words which you are calling sentence here, and each of these words are divided into tokens. Each of these tokens would have their word embeddings followed by their position embeddings, and now we have all matrix of this whole sentence with each row representing a single word. But at this stage we have that matrix what we just made. Now we are just cloning it 3 times. We are not doing any extra step. We are just cloning it 3 times. So the same matrix is here, here and here. And what's different between them is the weights attached to them. Weights are the thing which will get changed after training. So yeah, that's the only thing.
When you say weights are attached to them, do you mean there are like 2 matrices in here?
So what's really happening is we have our initial matrix here, and we have another matrix which is known as the weights matrix of query. So yeah, what happens when we go from here to here is those both matrices multiply between themselves, and we have another query matrix, key matrix and value matrix. So from our initial matrix we are dividing it to their respective weights, which constitutes and makes these new QKV matrices.
Okay. The initial matrix is a 2D matrix, right? M cross N.
Yeah.
And what we're multiplying it with is?
It's also a set of simple matrix. We also randomly initialize it at the start. It can be anything at the start.
It is also n cross m only, right? Or else like matrix multiplication won't be possible.
Yeah.
So now let's get into what query, key and value mean, and we actually do not exactly know how these things internally work, but we have somewhat of an insight which we can share. So yeah, let's suppose we have a social media networks and where we can send message to every other word or every other profile, let's say. So yeah, query is what am I looking for. Let's say you are on a dating website, your query is who am I looking for and who's the right match for me. So every word is like that. Every word asks a certain question to every other word. Oh yeah, am I related to you? Am I related to you? Are you the word I should follow, or are you the word should I follow? So yeah, every word asks such type of question to every other word. It's like posting a question on social media and getting a different answer, and see if there's any person who's compatible with you, and yeah, then get attached and do things you want to do. Okay. See. Yeah, like here the word it creates a query. I need to know what pronoun I represent. So yeah, it would ask this question to every other word and make sure that, let's say the sentence is the cat sat on the mat and it was comfortable. Now the word here it will refer to the cat, because yeah, cat sat on the mat and it was comfortable. Now we get to the key. So yeah, since we posted our question, key refers to our social media profile. Now what would other person see if he's seeing my profile, or if he's seeing my question? So let's say I post a question and person who's somewhat interested or not interested in me wants to know more about me. What he can do is just go to my profile and see all the stuff I posted there or put up there. So yeah, key is exactly that. Every word share information of itself, that it knows that yeah, let's say we have a word cat. Cat will share the information that I know for sure that I'm an animal. Yeah, every word share this type of information. So yeah, now we can query every word, we get a certain answer from every word. This is how things work. Value is the real answer. After the compatibility, the person would actually get to know that who he really is and who he really is not. So yeah, that is a very rich representation of every word. So like cat creates a very rich representation. I am a cat, I am a species of this kind, I am a female or a male or stuff like that. Cool. That is exactly what QKV means, and we can do different analogies for them. That one I can give you guys is, let's consider query as the query we put on in our Google search, and keys as all the links we get in our Google results, and then values are the actual content of each of these web pages. That's another analogy you can follow if you want to understand it that way. Cool. Exactly, I put it as like this. Attention is like speed dating for words. Every word is acting very fast and asking different question to different words, getting an answer, making sure who am I compatible to, and gets done with it. Cool. What we just discussed was self-attention. As you were able to see, what I showed was Da was asking question to itself and all the other words. Big was asking question to itself and all the other words. That was known as self-attention, and that is one part of how transformers work. But actually we have multi-head attention, which basically is, we have a single, I showed you the inside of transformer, we have multiple of these stacked on top of each other. We call single one of these a head. So multi-head means we have stacked multiple of these MLP transformer block on top of each other. Now I've put this sentence here, like let's say a single attention head was able to recover that the car is red, but it might miss the information about its size, because we are also giving a size to it, and also the information about its ownership. Multi-head attention help us exactly do that. So now each head specializes into a single information. Let's say my first head can specialize on color, my second head can specialize on who the owner is and the ownership things, and the third head can get the information about the size of it. That is exactly what multi-head attention is. It is basically self-attention, but done on the same sequence in a different way. So our first head can recover the information of the size, second head can recover the information of the color, third the ownership, subject, verb, and there's a tons of different of these heads. At start we started with 12 heads in the original paper, but now they have gone to like 24, 48 and a lot more. Cool.
One question. Does transformer able to detect itself how many multi-modal attentions he need to run for a particular sentence? Like one sentence can be small, one sentence can be big.
No. So these heads, as I mentioned that it started with 12 heads. This is a number which we can change or play with. We started with 12 because we had less number of resources, and this is very resource or compute heavy thing. We just decide on how much compute do we have and how much deeper do we want to process this. Because the more the layer increase, more the information we get, the better the model get. So it's not anything that model itself is recovering the information about this is the number of head I should go and play with this single word. So it's not like that. Every word goes to the same 12 heads, 24 or 48 heads. Cool. We discussed self-attention, then we discussed a superior version of it, if you want to call that, multi-head attention. But you must also have seen this cross-attention word. I'll give you a quick hint of what it is. It is basically, for here we were just focusing on a single language, which was English. But now let's say I want to train my transformer model on 2 different languages to able to help me actually translate between these 2. So let's consider them English and Hindi. Now that basically solves everything. Cross attention basically refers to getting keys from a single data source and values from the other data source. So yeah, we get keys from this data set, values from this data set, KQ which we just discussed, and then do the matrix multiplication between them. That is basically what cross multiplication is. It is not happening between the same data source, but between 2 distinct data sources. Cool. So now we are at the stage of this. We passed the sentence, the cat sat on the mat and it was comfortable. Now let's consider the word it. After it's passed to the, what it's called, the attention head or the attention block, it has the information that I might refer to cat in this sentence. It's 65% positive on that. It's 25% positive that I might also refer to mat and a tons of different things. But how do we concretely make sure that here we are referring to cat? I've given you guys a hint about this earlier in the talk. How do we do that? Like after attention, what are we supposed to do now? Yeah, exactly. Attention gives us this information, which I like to call as local information mixture. I would get back onto this, but yeah. Attention only works on the stuff which is passed on to a single run. Let's say the cat sat on the mat and it was beautiful, it was comfortable. So it has the information of the same sequence, but it's not really confident. So what we actually need to do is let it do or let it ask a tons of more questions. Since I made sure that I have told you guys that MLP constitutes a large number of neurons, then attention is, our MLP block would exactly do the same. So attention was like a group discussion. Let's say we all are sitting in a group and we are asking different questions to everyone if we are studying the same subject. We are somewhat sure that I have learned this concept very well, but how do I concretely make sure that I have learned? What can we do?
Asking ourselves like any question related to that.
Yeah, but that's what group discussion mean. So we need to do some self-study. MLP is exactly that. MLP is self-study, while attention is a group discussion. Now we are going to self-study the same topic and make sure that we completely understand it and we are able to use it further. So yeah, these are the words which we are not sure after it learned or not. Should each word just memorize what it learned? Should I apply the same kind of transformation? These are the things which MLP would help us figure out. Sure. We have seen the same image. MLP exactly looks like this. We have our input. We enlarge it and get into a higher dimension. This is because we ask it a lot of different questions like, are you a verb? Are you a proverb? Are you red in color? Are you blue in color? Each of these, let's consider each of these neurons asks this type of question like, are you a cat? Are you a dog? Are you an animal? Are you of this species? Are you not? And it is transformed into a bigger vector. After this rich composition we bring it back down to our vocabulary size since we are working with that. So that is exactly what happening. We are giving our input, passing it through our MLP. We are getting this bigger version of our initial input vector. We are then compressing it back to our original size and we are back to our vocabulary size vector. Cool. But now you guys must have question of why do we want to go bigger and why shouldn't we work on the same level? That's exactly what I've answered. Imagine you are trying to learn a very strange or complex subject, but let's say you are learning about division. Then you try to, it might remind you of subtraction or multiplication, that it's kind of relating to it. We are just doing the inverse of that. MLP does exactly the same thing. It asks a different set of questions, brings out different information that it already have and makes sure that I am able to get a very nice composition or representation of this exact word, and now I'm very confident that what I have or what all the information I have, I'm very confident of it. That is exactly what MLP does. Cool. We have gone through attention and MLP. It was, I think, the biggest part of his whole lecture. So yeah, you guys should have a lot of questions. Let's answer them. Cool.
The code I think would be nice. Probably not today. but
Yeah.
I think, we haven't really gone through any math right now, right? We understand there are probably matrix.
Yeah, I've kept it like that to not include any math, to just make sure that everyone gets the overall high level overview of how data flows inside and what are the simple formulas that we are working with.
And I think as software engineers, and let's say we think of doing this ourselves, Ratko. So is this hard maths or is this just matrices and multiplication? That's it.
Exactly, it's matrices and multiplication. The functions I've defined like softmax, you really don't have to write them yourself. We have libraries like PyTorch which does for us. So we have all this sorted out. I think the only mathematical operation I discussed was the attention, in which also we are just doing a dot product, which is basically just simply multiplying two vectors. So that is it. There's really no hard math in here. But yeah, if you go to the deeper, like how do optimization work, how do, let's say, in training back propagation flow the data, that might be a bit tricky, but at the core it's also just differentiation, which is done over like say 100 times. That's it. Cool.
There's one more doubt. What exactly is that math layer we have between attention and the ML?
What?
We have a layer which is on some mathematical operations.
You're talking about this layer now.
Yeah.
Exactly. So after every attention MLP block, we have a layer norm block. What it basically does is quality controlling. So it's making sure that no number is getting bigger, no number is getting smaller, and it's keeping them to, it's actually restricting them to stay in bounds and not go out of the bounds.
But if he founds any number which is out of bound, will he reject that?
No, it will suppress it down.
It will suppress it down. Doesn't that change the meaning of the whole?
All of these words will be suppressed down equally. So the proportion of the ratio of it would be the same. So yeah, that doesn't really affect the meaning of it. And let's say you want to do this in code too. It's already encoded into the module. You can just pull it up there. And if you want to get deeper, you have an explanation of the whole module. So at start, I asked you guys to forget this one. So now I'll come back to my analogy of how or why I would want to call this a highway. I like to call this a highway because then we can see each of these as a deroute or as a stop. So let's say we are at this stage and we just inputted our sequence of words. Now what it will do is go to the attention, and here it will get the information of everything, every word, what it means, and now it's come back to its original path and moves ahead. Now let's say it gets to MLP, it defines its own information, gets all things under the hood and get back to the main path. So what basically we are doing, we are not changing anything from input and output, we are just adding a different types of information. Like here we added some local information, while here we added some global information. Cool. I think we are at one question I would like to ask you guys: why MLP comes after attention?
Maybe because like we know like what to focus on.
And
we'll have more context about what that word is and how is it relating.
I want information from other data sets, right?
what?
I want to share my information, will get information from other
Yeah, so
data sets.
exactly. What MLP does is basically it refines the information it got from other words. But if we put MLP before attention, we really do not have any information to process or to work with. So if we just disrupt the change between this, it disrupted the whole transformer architecture and nothing works. So yeah, that's the simple question. Now I put local information gatherer and global information mixture. What is the apt word for this? Do you guys remember?
MCP.
Attention.
Yeah. This refers to attention. And what does this refer to? MLP. Now I would like to give you guys an example of it. Let's say we have a sequence of words or a paragraph, and in there's somewhere we have a football, which is defined as I have a big black and white football, big black and white ball. What attention does is this big white and black ball. So what attention does, it makes sure that, oh, the color of the ball is white and black, but it might be not able to get that, oh, that's a football. So that's why I call them a local information gatherer. Gathers the local information. They only gather information from the sequence they are given. While global information mixture or MLP, they have all the information from all the previous attention heads and all the previous MLP blocks. Now it knows there's a ball which is white and black, it knows the color of it, and it also from previous context it knows that, oh, that's called a football. That's why I've called them a local information gatherer and a global information mixture.
When you say from previous context, you mean during training?
No, from previous attention. Like let's say MLP at this stage have all the information of attention here, attention here, attention here, MLP here, MLP here, MLP here. That's what I'm saying.
Where does the previous training data come into picture?
There's no previous training data. It's from the same just before a.
I guess very similar question. The question is, उसको कैसे पता football क्या है? We've only told it this is a white and black ball.
But let's say we have an attention head here, which has figured out what football is. Now we are not rejecting information. You remember, right? We are going on a straight highway. We are just adding information on top of it. This attention head had it. Oh, there's a child might be playing with a football with his friends in a playground. This is the whole paragraph. But we, at this stage, the only attention only got that I have a white and black ball. What do that mean? And for attention, it's just that the color of the ball is white and black. But when it goes to MLP and it sees that, oh, the children are playing in the playground, there are a group of friends, what's the sport that we play with a group of friends and constitutes a ball which is white and black in color? Oh, that's a football. That's what's happening.
So if I have to repeat what you say, like if I go to attention, right, first attention knows that it's what is the color, like it has patches,
Yeah, exactly.
white and black, and then I'll go to another attention, it says I'm round and I might be used for a sport, and then when they group, like when they come on like the MLP phase, they will tell each other, okay, I am this, I am this, and
exactly.
then they'll combine and they'll say, okay, I think we are football.
Yeah, so like you remember in multi-head attention we discussed that each head specializes into something different. Same goes for every attention block. Every attention block specializes into something. It might be I am good at recognizing a verb, I am good at recognizing what a noun is and stuff like that. I am recognizing what is a sport, I am recognizing what is the color, everything like that. So each attention head is also specialized, while each each head is also specialized and each block is also specialized. Cool. This I have already told you guys. Attention is like a group study where we share information. MLP is a self-study where we concrete out the information and make sure that we perform well.
It makes sense to have multiple heads, MLP heads, because they are storing different information.
Yeah,
but why do we need attention at every layer? So like the way things, aren't we doing it in one step only?
Hey, let's go back to the diagram. Yeah, like what here?
So like MLPs, multiple heads are storing different information, so we need them. So attention are just a reference of how one word is attached to another. We are just performing some products and we are getting some information.
Exactly.
And we are doing it with different weights. So why do we need it at every step? Like after every MLP, is there a need of attention?
Let's say we are here. This attention told us about that the child's, there's a group of children that is playing. We pass on this information to our main highway, which then takes it to the MLP, which gives us information that they are playing a game which is played in group, which can be anything. Now let's say another head figures out that, oh, the color of the ball is red and black, white and black. Then it goes to the next MLP block, and which then figure out that, oh, this is a football. This way each attention is specializes into something, while let's say this is single head, which I'm showing you. And imagine there's, in the back of it, there's 12 different heads. 12 different copy of the same thing. Those also specialize into a single thing. Those are what heads mean, and this is what a single attention block is. So yeah, I've given you an overview of what my mental model is. I like to call them, instead of transformer, I would like to call them contextual machine. Because if we see our highway, we are at each step we are just adding some more context to our initial information. Like here we added something, here we added information about position, here attention added something, here an MLP added something, here attention again added something. So I like to call them attention machines. And you can see I have put an addition sign here. That is, I'm calling a gate here. Like in your engineering class, you might have heard of AND gate, OR gate. I've called this the context adder gate. So it is basically just making sure that I am adding all the context I'm getting from the positions to the main highway. I'm adding all the context I'm getting from the attention to the main highway. So to make sure that I'm not losing any information, but just making more information on top of it. So yeah, I just think of it as a contextual machine. That's a simple note from my side. Cool. We have gone through attention, we have gone through my idea. So now let's discuss on the training and inference, which you guys have been asking for a lot of time. So what happens while training is, let's say this is the whole thing we want to train our transformer on. So yeah, we'll show this the full sentence while training, but what happens at inference is we'll only give us this word and make it figure or generate the next follower word. That is the whole crux of training and inference. At training we show the entire sentence and ask it, let's say it says the first word and its goal is to make sure that it identifies cat. Let's say it identifies or generates set. What will happen is we'll send it a wrong signal or a negative signal, which from back propagation teaches it that, oh, this is wrong and I should predict something else. At the next time, let's say it predicts cat, that is also wrong. So it figures out, no, neither does sat work, neither does mat work. So let me try if cat is the right thing that fits here. By this process of learning and doing wrong, learning again, it learns the training and it basically learns how to generate things which make sense. At the inference time, we just give it the thing we want to start it with. So this is the initial thing we want to start it with. So now what the next thing is, it should predict what the thing we trained on. So now here it would confidently predict the next word is mat. Predict what the thing we trained on. So now here it will confidently predict the next word. Yeah, the training is happening via back propagation. Let's say we are on the cat. Now the next word we know is sat. So that's the only reason we are keeping the whole sentence in the training method or the training mode, because we want to make sure that we calculate the loss from the right value of it. Now we know that mat is not the right word here. So what our algorithm or our loss function would do is that, oh, you predicted that wrong, let me give you a very negative reward, so that you understand that you have to tune your parameters or weights in a way that the next word is mat. So that you understand that you have to tune your parameters or weights in a way that the next word is mat.
And
so
this training is applied on like all of the heads combined together, like the whole
from here to here, everything has weights and all of them. So remember at initial times we initialized everything with random values. All those random values get changed as the transformer trains. So yeah, weights attached to attention changes, the query key value weights changes, weights for these embeddings changes, positional embeddings, everything changes after each step of training. Cool.
So basically, can we say like weights are what determine how what
exactly. Weights are exactly what we mean by, if we are saying we have 20 billion parameters, these parameters are what our loss function can tune and make sure put in the right proportion to get the stuff of it right. So yeah, we are only training these weights to make sure we are generating the right stuff. The same goes for every generative AI. I'm not including diffusion and other stuff, which is, yeah, I'm not including diffusion here, but for audio, for video, yeah, it's happening like this. Here we would have our embedding weights and here we would have our attention weights. These weights are completely different, but at the start they might be same because we are randomly initializing them, or they might not be the same. What happens after training is these weights, as we understand what query keys and values are, they ask the right question, gets their weights changed and stuff like that. And then after, let's say the sentence is the cat, now we know the next word should be sat and it should predict that. But for some reason, let's say it predicts something else. Now what we are supposed to do, our loss function will give it a very negative reward. So for everything in this system, every parameter will get changed just to make sure we are not getting a negative signal again.
Let's say there is more information stored. If I talk about, for example, GPT.
That is a very hot research topic. Like in this whole thing, where is memory? Like there's no stage where I'm storing memory. How is LLM able to recover all these things? For that exact reason, I've shared you guys the insights of the local information gatherer and the global information mixture. So basically, these feed forward or MLP layer, as we know, are the things which are said to constitute all the information or all the memory of this whole transformer architecture. So these are the main culprit of all the information we are storing. We have, let's say for now, we have only this thing we want to train our model on. When it predicts let's say we give it the input of its goal is to predict cat, but for some reason, let's say it predicts sat instead of cat. What would happen here is our training algorithm, which is our loss function, would give it a negative score that, oh no, at this place the word should be cat, but you predicted mat. So there would be some mathematical negative function, negative signal for it, that no, you have to change your parameters to make sure that the next word is correct. But at any stage, we are not showing LLM the next words to it. Like when we are asking it to predict cat, we are not showing it the full sentence. So we are only passing it this, but we actually know that the real value of this is what. But while inference, we actually do not know what the next sentence or word is going to predict. Cool. Anything else? The scale effect. So in 2017, attention is all you need was first published. It constitutes of 12 attention heads as we know of. But at the current stage, what happened after that is a lot of these companies started to do crazy things, and the first thing they tried was to let's multiply this number of heads we are doing, let's do more of these attentions tagged or MLP, attention and MLP. And what do that give us? It gave us very phenomenal increase in all the performances. Everything went, and yeah, every chart was up. So with that we get to know that scale is real. Whenever we scale something, let's say the parameters or the heads, we are getting more information or we are getting more smarter models. So that is basically what the scale effect is. We scaled down all the attention heads, we scaled down all the attention parameters, we scaled down MLP weights, MLP parameters, and we also scaled down our vocabulary. We scaled it up to a lot now. I really don't know what the figure is right now. But yeah, after all the scaling, we now have much more smarter models. As you guys were also able to see from GPT-3 to now GPT-5, our models are much more smarter and doing a lot of things. So that is basically what the scale effect is. There's a very nice, I think, answer for that is, even if you have a single very unperformative neural network, but you train it for a very large time with a lot of compute, it would actually beat all these transformer and all these new models. But it's just that we do not have the actual compute needed to do that. We are very short on compute, so that's why we have to do these things under the limits. And we have, by time to time, we have found some crazy optimization tricks which gives us some boost. One of them was recently when O series came. We saw the thinking pattern emerge, the chain of thought emerge. So yeah, that was the recent thing which happened. Yeah, the better the hardware, the more we can process this information, the better the things get. That's what the scale effect says. Like for Moore's laws says that every year or every 2 years number of transistor doubles, but we are not sure about the factor it multiplies with. Let's say we have X number of GPUs, how much our model gets smarter. So we do not have the exact value for it, but the scaling paper shows that if you just scale anything, it is going to perform better. Yeah. So now we have gone through the whole flow of it, that how a transformer takes input, processes inside of it, and gives us an output. Now let's discuss what current things are going on. As I discussed, O series gave us reasoning, but they didn't really open source it. What really gave us a part was this GRPO function, or I would like to say the GRPO paper, which DeepSeek released with its R1 model. So what this function basically is, it basically is a RL function, which stands for reinforcement learning. So it learns all these things of this reasoning process. Reasoning process basically stands for chain of thought. So the model internally makes a different chain of thought of how should I answer this question. So yeah, GRPO is basically doing that same thing, and it's just a way for us to evaluate it. And RLVR stands for reinforcement learning with verifiable rewards. Here verifiable rewards means something which we can verify programmatically, which are, let's say, math functions which we can verify. If there's sum between two numbers, we can programmatically verify that. So that is exactly what RLVR is. If we have a verifiable reward from our model, we are giving it a positive reward, which enforces it to do the same thing again if it faces a similar question. The next thing is MOEs, which are known as mixture of experts. Now we guys hear that DeepSeek released a 600 billion parameters model, a 800 billion parameters model, but they also say it activates, or there's only 22 billion layers or neurons activating at a single pass. What do they exactly mean by that? That is what MOEs are. MOEs are a different, so we discussed attention, the transformer block. In here we have installed a router. Now what this router does, it basically routes these to specific attention agents or attention blocks which are experts in different fields. For now, let's consider we have 4 different experts specializing in math, science, chemistry, and geography. So whenever this router feels like, oh, this is a question for geography, it just routes it to the geography attention head. What it basically does, the attention parameters or all these other 3 parameters or all these 3 heads now gets activated. So at a single pass, only a limited amount of number of neurons get activated, rather than when, as we just saw, that if we do the same thing here, all of the parameters or all of the neurons would get activated. But with this, only a smaller number of parameters gets activated at a single pass. So that's what they mean by that. Oh, this is an 840 billion parameter in total, but at a single pass, only 22 billion parameters of them are getting activated. Tool use are everything. We are using this every day. If you guys have seen that ChatGPT can now search, it can search the web, get the right things. This is basically just a very simple thing any software engineer would do, is to basically give it access to APIs so that it can call other things and get information from it. And it is now heavily used. We got something like MCP, from which we can make literally any tool we want for Google Docs, to for AWS, which we can use to just send, let's say I want to start an EC2 instance. We can make an MCP of AWS attached to our language model and just give it a command there. This multi-head latent attention is very similar to GRPO, also given by DeepSeek. This is very mathematical thing which gives us optimization. So only this word is new to us. We know what multi-head attention mean. What latent mean in machine learning is a compressed state. So we have let's say we have a very big data. We compress it down to something of very high dimensions, but it is very compressed. That is exactly what latent mean. What DeepSeek or the researchers at DeepSeek did, let's say we have query keys and values. What they did was they took 2 of them and suppressed them down. So they made a latent space of them. Now instead of going back and calculating these 2 things every time, what they did was just go to this latent space we just created and get it from that. That is what multi-head latent attention means. It is just a compressed state. Instead of getting the QK transpose which we just saw in the attention formula, is now represented by the single compressed state which the model can go to and pull out the data it wants. That is what. There are a lot of different things going on from that, but yeah, for language modeling, these are the main things that's going on currently, and let's see what's get ahead. Cool. That was the session. If you guys have any question or any doubt from any of the slides, we can discuss that. Anything unclear?
Yes, sir.
क्या?
जो MOE है, उसी के थ्रू हम smaller models निकालते हैं. Let's say when we say we get smaller models out of it.
That is no, MOEs are not that. That's a different thing. Let's say we train a very big model. You guys also see that DeepSeek released 840 billion parameters, but then it also released the same version of it with smaller parameters. How does it, or how do they do that? So from the very big model they call it a teacher model, and they make a small model with very less parameters, let's say 20 billion parameters in compared of 800 billion parameters. They create this smaller model. Now this model is called as a student model, and the bigger model is called as a teacher model. This student model asks different questions to this teacher model, and this teacher model, which has very large intelligence than the small one and more information, more context, it gives answer to every question of this small model. By this process, the small model is able to learn or very closely mimic this big model. So that is how we get the smaller models.
One implementation doubt I have is how can we combine the response of multiple heads that we are getting?
Okay, nice question. Yeah, so here, this is a single head of attention. What we were doing is we were passing it embeddings, input embeddings. But let's say we now have 12 different heads. What we do is we divide this input embeddings into 12 parts. Each of these heads attends to this input head divided by 12 of its parts. And at this stage, when it's about to give the output, from all these heads, we bring the final output vector and combines them back, so it gets back to its original shape. So if let's say we have 12 heads, we are breaking it down into 12 different parts. We have 48 heads, we are breaking it down into 48 different parts. And at the top of here, we concatenate all of these different vectors, make them come back in their original styles, and work with our vocabulary and give the final output, which is just another probability distribution graph, from where we can choose our selecting style. Either we want to be greedy or we want to be a little more creative. Cool. Any other questions?
Can you brief a little about the chain of thought?
It's okay. It's very so we try to mimic what a children or a human does. Let's say we give anyone a question of what's 2 plus 2. Instead of what model were doing is they were, as soon as they got the answer, they started the inferencing and just give the final output. So that was the whole thing transformers were doing before this. Now we give them the power to pause for a while, think what you are going to answer, and just verify that if you are doing is or what you are doing is right. So let's say in fast you might have seen that models responding 9.11 is greater than 9.9. How was it doing that? It might be doing from the tokenization style. Like at the stage where we were tokenizing different words, let's say tokenized 9 as different and point as different and 11 as different. For it together, 11 is a big thing than 9. So for that reason it was responding that. But now since you are giving it reasoning or time to think, it will think that, oh, the whole thing is 9.11, which if I go to decimal spaces is 0.11, and if I check this decimal space is 0.90. 0.90 is definitely bigger than 0.11. That is why I'll answer the correct this time, which is 9.9 is bigger than 9.11. That's how the chain of thought works. Cool.
Can you tell like how they memorize? Like first, if the prompt is like the cat sat on the mat, and they response like, and after the second response, I just say now cat sat on the floor, something like that. So how would they memorize like changing?
Yeah. So now what our attention would do is again calculate all these things and we'll figure out that now the cat is sitting here, and since we are passing all the previous context to, it would remember that what we are doing is simply again passing all the things from the previous context along with our new thing which we have asked. So it would know that, oh, previously he asked that the cat was sitting on mat, but now the cat is sitting on tree or somewhere else. It would figure that out. So
Is it part of LLM layer or implementation layer?
What?
Are we just storing that data somewhere else?
No, we are not storing the data somewhere. At each turn, let's say we are doing a very long conversation with ChatGPT. At each turn, we are passing everything again back. That's why these LLMs are called autoregressive models. By what I mean is that at each stage, we pass everything just to get the next generation. Even if we remove anything from this previous context, the model would fail miserably.
But like there is a large sentence. In that sentence, I talk about like a cat part only, and when I change about the cat, like they are sitting in somewhere, and I talked about something else on that from that one. But the attention would be sending whole like earlier part as well, not on the cat part. Like
We discussed that attention was the cat sat on the mat and it was comfortable. Here we focused on it, that how it would correlate that I am referring to cat here and not mat. Let's say we get a bigger context. Again the same thing would happen. Now that it would see, oh, at this till this stage of the user prompt I was doing this, but now I am doing next another thing. So now let me work with it. I'll pass this information to the MLP block, which will then figure it out globally that, oh, the state of the cat has changed and now it has moved somewhere else. Okay, cool. Okay, I think you guys have no questions, so let's finish up. Thank you guys.